Hello, everyone. Welcome to our unit, or the rest of our unit, I should say, on proof writing. So today is an introduction into what a proof is, okay? A proof, as simple as I can explain it, is a math essay. So an essay for math class. So in our proofs, we're going to start with some sort of introduction, go through a couple paragraphs, quote unquote, in order to arrive at a conclusion. So in this picture, just to kind of push us into congruent triangles, meaning one triangle congruent to another, we're going to roll back to rigid motion here. So for each diagram below, determine which rigid motion, reflection, rotation, and translation, and again, that was our unit 2 topic, maps one triangle onto the other. Since rigid motions preserve length and angle measure, solve for the indicated variable. So looking at this first diagram, this triangle on the left corresponds to the triangle on the right. So we always have two shapes here. And how one mapped onto the other is by a reflection. So I'd like you to be trying the next 3 examples on your own. And since it's a reflection, that this purple triangle can reflect and kind of flip over. If I fold that over, that means this 2x plus 10 corresponds. So 2x plus 10 corresponds to the same position, the 30. So that means they're equal. So corresponding parts, remember, are equal. Right? So in that case, we would solve for x. So we would subtract 10 from both sides. 2x is 20, making x 10. So I'd like you to be telling me what rigid motion maps this first triangle onto the second. And since that happens, this right angle is still equal, this side is still equal, that side is still equal, and so on. Okay, so that's the second question. What rigid motion would map triangle 1 onto 2 for number 3? And how is this triangle mapped onto this triangle? All right. And if I tell you that this is A, I'll tell you that's A prime over there. That helps. All right. So with that said, I would like to move forward to some proofs on the back of this. So these are called algebraic proofs. And we've done these in the past. You did these a little bit in algebra, but how I'm going to explain this is these proofs start with your given information. And if I kind of equate this to an essay, the given information is like your introduction. So your introductory paragraph is what we start a proof with. So we started by given the equation 4x plus 5 equals negative x minus 17 over 2. So that's our introduction. Since that was given, the first reason in our proofs is always the fact that that information was given to us, that equation was given. They ask us to prove that the x value is equal to negative 3, so that this side of the equation equals this one. So the math that we do to get there is because of certain mathematical properties we have. So how did I get from a 4x plus 5 equals this fraction to 8x plus 10? Well, this 4x plus 5 got doubled. And how did that get doubled? By cross products, okay? We cross multiplied there. If you think of this as a proportion, that 2 got multiplied there. So I'm going to say multiply, M-U-L-T, P-L-Y. Sorry, can't really spell today. Multiply, here's my L, by cross product. So that's how we got from step 1 to step 2. Now we're going to decide how do we get from step 2 to step 3. So why does 8x equal negative x minus 27? So how did I get from 8x plus 10 to this 8x equals negative x minus 27? Well, that 10 got moved over. So since we subtracted 10 from both sides, That's called our additive inverse when we add the opposite. So that's your additive inverse. And that was a property, again, you did back in algebra at the beginning of last year. And then what about here? From 8x equals negative x minus 27, how does that go to 9x equals negative 27? Well, that x combined over. Okay. So I'm going to call this combining like terms. So again, how these proofs work is, how do you get from here to here? Well, we multiplied by the cross product. How did we get from here to here? Well, we added over the opposite, additive inverse. How did we get from step 3 to step 4? Well, we combined like terms. Now, how do we get from 9x equals negative 27 to x equals negative 3? Well, we did division, right? We divided. So this is called the multiplicative inverse. I'm just going to abbreviate mult inverse. There. And that's a proof. How do we get from this equation to this answer? Well, we did all of these math rules, okay? In order to undo the division, we undid the addition, we combined the like terms, and then we undid this multiplication. So this is just a format of how we get from the equation to the answer. So we're really explicitly explaining really how we got from step 1 really to step 5. Now, some of you might have done a little different thing in between, but this is one way to have done it. So just like an English essay, you can have 18 different English essays on the same topic that read a little bit differently, but they're all correct. Same with these proofs. You could have done one step a little differently than another, but we still get to that same x value as an answer. So again, this is a math essay. We're given the introduction, and what you're asked to prove is what we end with is a conclusion. All right? So that's how essays work, or math essays, I should say, how proofs work. So looking at number 6, so that was algebra. That was x's and y's. We don't really know why there, but x's and numbers. And we got to an x equals. Here's a geometry proof. Okay? We start with a picture. In this picture, they tell us that the measure of angle 1 and the measure of angle 2 is 100. Those are our rules. So our given information are the rules we go by. We can't make anything else up. Now, this picture almost looks like a right angle, but they don't tell me that in my rules. So I can't use that information. It might look true, but we can't assume it true. So remember, we have no assumptions here. And yes, the word ass is there. We can't assume anything. That's bad. Okay? ASS is going to stand for angle side here soon. But no assumptions. So it might look like a right angle, but unless they tell you it in the given set of rules, okay, we can't make that true. So angle 1 plus angle 2 is 100, and the measure of angle 1 is 80. Well, if I know that this is 80 and the whole thing is 100, then angle 2 must be 20. But how did we get through there? How did we get to that process? So again, the first 2 statements in our proof were part of the given, right? That information came from here. The given information is this. So statements 1 and 2 are both given to us. But how do I get from those statements down to here? Well, if measure of angle 1 plus 2 is 100, and measure of angle 1 is 80, well then 80 plus angle 2 is 100. So what I did is, since 1 equals 80, couldn't I put 80 in for 1? What do we call that? When we take one number and put it in for its equal, we call that substitution. So that's a reason of our proofs. So these reasons are simple properties or definitions that come back from our notes 3.05 from last time. So that last page of notes that you completed last time, these are our rules. These are our geometry rules, okay? So substitution is really an algebra one. That's going to come up kind of often that we're going to use. But now, how do I get from statement 3 to 4? How do I make that 20 appear? Well, if 80 plus 2 is 100, how does that 20 appear? Well, we subtracted 80 over, didn't we? So again, that's our additive inverse. We used it up here. We're going to use it again down on this proof. Additive inverse. So those are two proofs. We have an algebra proof where we're given certain information and we have to argue our way to a conclusion. Same thing with the geometry proof. We're given a set of rules to go by and we have to argue our way to the conclusion or the proof that they've asked us to end with. All right. Moving on to some other notation information. So today's notes are fairly quick, a couple pages here. And then the next page, I want you to be writing your own mini proofs. And that's where you're really going to need these boxes from last time. Okay, so these kind of line right up, and I'll give you a couple clues into that when we're done. Some important notation is these words and symbols. Notice AB is written 4 times here, but each way it's written, it means a little something different, right? So this first one is talking about a segment. There's no arrows there. So this is a segment from A to B. A segment from a point A to a point B. AB, if you look closely, there's only an arrow on one end here, okay? So this is a ray starting at point A and continuing through point B. So if I were to sketch a picture there, we would start at A, we would have point B on the line, and the line kind of extends through B. AB as endpoints might be this diagram here where we start at A and end at B. So a picture kind of goes with the notation, is this out in words. Angle ABC. Well, some of you are just realizing that this letter B is the middle letter in our angles. But if we have an angle, there's 3 points on the angle, A, B being the vertex, C. So B is the vertex of that angle. So I'm talking about the angle formed from a point A to a point B to a point C. So this is just saying angle ABC. Letter B over here, there's 2 arrows on the end. So that would be a segment from A to B, but it extends in either direction beyond A and B. So this is a line. Let's use a capital A, B. Whenever we use points on a line, we use capital letters. AB, this actually means the measure from A to B. So if there is no bar over the top, we're talking about a measurement. So AB equals 10 might be a segment from A to B that's 10 inches. So when we talk about a measure, we don't put the bar over top like we do over here. And same thing here, M of angle ABC, they might talk about the measure of angle ABC. Okay. Special notations, equality versus congruence. When we talk about equality, we're talking about measures being equal. So I'm going to talk about these diagrams here in purple. So I'm almost going to color code this. I'm going to use 2 colors. I'm going to use green for congruence. And these are generic. So measures, here we know that the measure of AB is 10 units and the measure of CD is 10. There's a 10 on each of them. It could be feet, could be inches, depends on the scaling. Okay. But we would say AB equals 10 and CD equals 10. Therefore, AB equals CD. We didn't put the segment notation above top of that on purpose because we know those measures of AB and CD. Okay. Same with angles. Now down here, this diagram gives angle measures for angles K, J, and L. So I know that the measure of angle J, the measure of angle at J is 60 degrees. Now I could also call that same angle the measure of angle KJL is 60. So again, this is an equilateral triangle where we know the measures of all the sides. Okay, so when we have a number value added to it, we use the measure of an angle symbol, and we don't put the bars over our ABs and CDs there. Okay. Congruence is a little different. So in this diagram, we're going to talk about congruent pieces. So these two diagrams kind of go about measures. This diagram goes about congruence. Now, congruence is generic. It just says that this little dash mark tells me that AB and this dash mark AD are congruent. So when we talk about congruence and we have segments, we are going to say AB as a segment, starting at A, ending at B, is congruent to AD. We also know by this double dash and this double dash that BC is congruent to CD. Okay? So segments get the tilde. Notice over here, no dash over it, no squiggle, no dash. So equality, no dashes. Congruence, bar, squiggle, bar. All right. So when you have the extra squiggle, you need the bars over the letters. And when we're talking about congruent angles, this little arc mark and this little arc mark are telling me that those two angles have the same measure. We might not know it. It might be 30 degrees. It might be 32 degrees. We don't have an exact measure of it. So what we need to do here is just say that angle B is congruent to angle D. Now notice I didn't put the little M in front of those, and that was on purpose. Right? So that's just some notation about congruence or measures. When you're given measures, we use equality. When you aren't given a number, numerical value next to your diagrams, we use congruence. Figures are congruent. Numerical values are always equal, is really what I'm trying to say. And I'm glad I put that there in print. When adding, subtracting, multiplying, or dividing segments, use an equal sign. So looking at the correct notations here, this first notation, when we're doing our proofwriting, notation is important. Bar of MA, so this says segment MA is equal to segment TH. That is incorrect as it's written. So this one is wrong. If we add the tilde, that makes it correct. Okay, so it was wrong. So I'm going to cross that one out. Please circle the correct notations if I go back to those diagrams. So segment TH is congruent to segment MH. That is correct. When we are adding things, we use equality, not congruence. So this is wrong because this should be equal. So this is correct notation, that the measure of MA plus the measure of TH equals the measure of MH. Triangles are figures. Figures are congruent. So if we're talking about a shape, triangle lap and triangle dog, okay, figures are congruent, not equal. So again, figures are congruent is kind of the idea there. Okay, so we're going to come back to more of that notation later. But looking at, did someone make a mark? So these little markings on your diagrams mean something. And this is where I need us to go back to this segment rules sheet. This was the last page in your packet. After your quizzes last week, you should have had this filled in. And a couple important pieces here is if you have a bisector, you have something split into equal segments by definition of bisector. If you have a midpoint, parts are congruent by definition of midpoint. When you have a triangle that kind of shares a side for reflection, you have sides that are reflexive. So if you didn't fill this in, if you can pause the video here, make sure this sheet is filled out. We're going to need it. There's a little bit more at the bottom. If you'd like to pause again. And the back page. If you did not complete this, it's a little bit longer. Here's the beginning if you'd like to pause this or go back and watch the 17-minute video so it makes some sense to you. And there's one more piece. Here's the bottom of that, where we talk about parallel lines. There's alternate interior angles, corresponding angles, and alternate exterior. Okay. But these markings mean important information. So what did somebody mark? So this first picture, these little arc marks here and here are telling you that there's a set of angles. Okay. So looking down the word bank, what angles do we have? Do we have reflexive property, congruent segments, alternate interior angles, perpendicular, bisector, vertical angles, or parallel lines? There's only two cases that talk about angles, and these two angles are vertical to each other. So we have to recognize that. So those are vertical angles. What is this the marking for? That box there. So we've used vertical angles. That box is for perpendicular lines. So remember that perpendicular symbol if you need to write that next door to it. This marking, a little dash mark here and a little dash mark there, is congruent segments. It's just saying that that measure, whatever it is, and this measure would be equal. So this is congruent segments there. In this case, this segment is coming in and creating equal pieces. This segment is coming in and creating other equal pieces. So is that our reflexive property? We've used congruent segments. Is it alternate interior angles, bisector, or parallel lines? Okay, so this is going to be a bisector. This segment is bisecting it, the angle. And this segment here, this purple segment, is bisecting the segment given. So that was a picture for bisector. This diagram is reflexive. So I like to put an X on it so I remember the word reflexive, which has an X in it, right? So I kind of changed the marking that was there. And last but not least, we have two boxes left, and I believe we have two words left. So these angles in that Z, so remember our Z angles? Okay, if you kind of draw in the Z with me there, those are alternate interior angles. And that's because of these arrows here are telling us that the lines are parallel. So we've now used all the words from the word bank. So those markings we have to get used to. Exercise 3. Based on the markings in the diagram, please write 3 congruent statements that list the parts of triangle ABC that correspond to congruent parts in triangle DEF. Correspond means a single dash and a single dash. That means those segments, those are markings for segments, are equal or are congruent. I'm sorry. So again, congruence is what we're thinking here. So we're going to have AB, bar across the top, is congruent to DE, bar across the top. So I just started with the segments. I could have started with these angles. So since there's a single arc at A and a single arc at D, angle A is congruent to angle D. And again, I don't put the M's here because that's not how we notate this. And last but not least, the other set of parts that are equal is this angle at E and this angle at B. Now, instead of using single letters, we could use the 3-letter combination. So angle ABC is congruent to angle DEF. Now, how I decided on what order these letters go in is based on their pieces that correspond. A and D are in the same position. So I started with A and D. Then I kind of went over to E and B is the next set of letters. And then C and F would end up being equal pieces as well. Because if we know these given measures are equal and these given measures are equal, by the rule of 180, the last two angles would also be equal. I know this is a lot so far. And again, if you're coming into class later this week, I will really try to explain this a little bit better. I know I'm going fast right now. But again, I try to keep these videos short and sweet. If you need to pause and re-listen, please do. But looking at proofs 1 and 2 down at the bottom of our screen, I'm going to start a diagram of triangle ABC. So this given information, and this is a setup for a proof here. We have a statement column and a reason column. So we have what's called 2-column proofs. Statements is your first column. Reasons is always going to be the second column. And our given information here is that in triangle ABC, angles A and angle C are congruent. So if I draw a picture, if I know 2 angles are congruent, I know it's going to be an isosceles triangle. Okay, so I put A and C at the bottom of that picture so that A and C are equal. Well, if 2 angles are congruent, then I can conclude that 2 sides are congruent. So I have to decide which 2 sides are equal. Well, if I put A and C at the bottom, then AB, this side, and BC must be equal, right? Because B is the vertex angle that's not equal to A and C. So again, in a triangle with 2 equal angles, I know for a fact it's going to be isosceles. So this reason, if you know 2 base angles are equal, we're going to know that the sides are equal. And the sides are equal based on what's called the isosceles triangle theorem. We're going to have another notes page here soon about that isosceles triangle theorem. But the theorem says if 2 angles of a triangle are congruent, the sides opposite them are congruent. Instead of writing out that full sentence, we shorten it up to say this. Proof 2. We need to draw a diagram based on this given information. So here lines CB and AD intersect at a point E. So remember lines have arrows at each end. We're going to put A and B on the first line. And, C and B, my mistake. If I reread that, Ms. Locke. And A and D is the second line. Now, D could go at one end and A could go at the other. The diagram isn't all that important. But those 2 lines, again, that extend infinitely in 2 directions, meet in a point E. Okay? So when we have intersecting lines, going back to our boxes here, when you have intersecting lines, we create these vertical angles. So lines that intersect at a point create vertical angles. So we have to kind of mark up our picture to decide which angles are right. Which angles are equal. Well, this angle here, I'm going to put a little 1 in there. And the angle over here, a little 2 in there, those angles are equal. So I like putting numbers in my picture. I don't like this 3 letters stuff personally. I like to use these numbers. So when you put numbers into your diagram, like the 1 and the 2 I just did, then you can use those in your proof. Okay? You can refer to them as numbers. So if you have lines that intersect, angles 1 and 2 would be equal. I could have put 1 and 2 up here and down here. Those are also vertical. This angle, maybe if I put a 3 and a 4, both sets of angles are equal. Depends on what we're going to need for our proofs. But the reason is that vertical angles are congruent. So again, I explained this boxes page and this intro to proofwriting. These are like our vocab lists, okay? So when you're given certain information, now these letters are going to change, but this statement here and reason, okay, the statement is in the first column, the reason is in the second column, is identical to what I wrote here, okay? So I just kind of copied this statement and reason based on the same given information and pasted it here. So again, these are like vocab lists. So that's how I want you to understand these mini proofs. So these mini proofs, there's about 5 of them. I'm going to give you the first statement and reason here. C is the midpoint of AB. So we're going to take the given information and we're going to put it as the first line in the proof, given. So you're going to go through and do that for each proof. So this given information becomes the first line. We rewrite it. BD is a median. Here we're going to rewrite it. Statement 1, CD is perpendicular to AB. Okay. The reason 1 is always given. Just like in an essay, you rewrite your thesis in the first paragraph, we rewrite our given as the first line of our proofs. So you're going to do that for every proof. That's at least half credit for today's classwork. Statement 2 is creating a conclusion based on that information. So if C is the midpoint in this picture, then I know this segment AC and this segment CB are congruent. So my conclusion is that CA is congruent to CB. And if I have the word midpoint, I'm going to go to my boxes page and I'm going to find midpoint. Well, in this picture, we had ABC. So that's where AB was equal to BC. What was my reason? Definition of midpoint. And guess what my reason right here is going to say? Definition of midpoint. Now, median is not on those boxes, so this one is actually kind of new, and this is really to see if you're watching my whole video. If you have a median connects a vertex to a midpoint. Now, there's a unit I had to skip this year because of COVID. We couldn't do our constructions unit where we would have found out what median is before now. But I'm going to tell you that if you have a median, it connects a vertex to a midpoint. So in our diagram, BD is a median. What does that mean? It's going to mean that D is a midpoint. And why is that true? Well, because the definition of median just said that. So how we write that here is definition of median. So how do you get from some information to the next information is by some sort of definition. And again, that's from your boxes page. When you see the perpendicular symbol, you're going to go to your boxes and you're going to write down at least one of the conclusions using the letters from your picture here. So since CD is perpendicular to AB, I know we have 2 right angles. Now I put the 1 there. 1 is talking about the angle to the left of that point D. So what I can say here is that the measure of angle 1 is 90. And then that reason is going to come from your boxes. Okay. So again, when I say boxes, I mean these boxes. It's like your vocab list. All right. Good luck. Try what you can. Again, the first statement and reason is just rewriting that given. All right. Thank you, and we hope to see you